Good afternoon, everyone. If you haven't picked up your midterm yet, please come see me after class. I'll give it to you. Otherwise, I'll assume you're not here today. So we're going to start on a new unit, which is going to be another take on classification that's going to work a little bit better than the logistic regression model we studied. And in this unit, we're going to work with the famous MNIST digit classification data set. So here, the goal is if you're given a small little image of a handwritten digit, the goal is to classify which digit it is. So there's digits 0 through 9 are in the data set. The images are 28 by 28. They're not color images. They're what we call grayscale images, where every pixel value in the image just has a real number. In most cases, it's an integer between 0 and 255 that tells you the brightness of that pixel. So so that's what the individual data samples are. So you have the features then would be this 28 by 28 little image. And there's 70,000 examples in this data set. So it's a healthy number. This was collected in the 1980s by the American Census Bureau. One of the motivations was to be able to automatically read the zip code on handwritten letters, which is something that before that time had to be done manually by humans. So they wanted to automate that. So this is a very famous data set for machine learning. Let's say if you have a new method and you want to try it out, this is a pretty famous data set because it's relatively simple, it's widely accessible, it's not too big, it's not too small. There's many benchmarks for it. And so this is built into the sklearn data set, so we can get it directly from sklearn. And when you download the data, here you can see the dimensions, 70,000 by 784. And this is because each of these images is actually represented in a vectorized form. So all the pixels are just stacked in a long vector, and then 28 squared is 784. So that's where that number comes from. Okay, so here's a little table of pretty recent benchmarks from Wikipedia. They're probably not updated very frequently because this particular data set is not something that people really try to do very well on. It's just sort of a toy data set in some sense. So, but if you look at the entries, you have these different models. Like this is from best to worst in here. And so you have things like convolutional neural networks that are getting an error rate of 0.17%, so less than 1%, all the way down to linear classifier, which is getting 7.6%. And when you look at what we're going to focus on in this unit, it's the support vector machine. This is doing 0.56%, which is not too bad. You know, it's certainly not state of the art, but it's not too bad. So this is sort of a partial motivation as why we're going to study it. It's a very famous idea. We'd like to know more about it. So first, let's just talk about some of the basics. So I mentioned that the data set comes with these 784 dimensional vectors, and the way that you do that is you can go back and forth from these images to vectors and back very easily in NumPy. So in NumPy, there's 3 different commands that can take you from something like this, which you can think of as an array or a 2-dimensional array, to a 1-dimensional array here. So one of them is ravel, one of them is flatten, and one of them is reshape. And the reshape command is a very general command. So like the reshape command can be used to come back in this direction. In this direction, you have to tell it, how you're going to reshape that single array. And so here we're saying reshape it into a 28 by 28 matrix. But if you're going this way and you just give it the number -1, that basically means reshape it into something of one dimension, and you should have enough information to figure out what the length is yourself. That's sort of the -1. It's sort of like just use the value that makes sense. And so since NumPy knows that this is 28 squared, it knows it's going to reshape it into a 784 length vector. Okay, so that's how we can go back and forth. And just a comment that in NumPy, vectorization is done by stacking rows, whereas in some other languages like MATLAB, it's done by stacking columns. And also in most papers and books that you read, vectorization is done by stacking columns. So that's something to keep in mind. So for example, if we're talking about papers and books, we would have, let's say this is the matrix. And if you want to vectorize that matrix, you could say vec x, big X, that's going to give you a column vector. And what it's going to do is it's going to take that first column, and then onto the bottom of that, it's going to stack this next column and so on until the very bottom, it's going to stack that. And then you will eventually have something here that goes from x1 all the way to 784. So my point is that if you're actually doing this in NumPy and you're not careful, it will actually take this and then stack that next to that and so on. It does it row-wise. So just be aware of that. So if you want to describe what NumPy is doing in the standard textbook form, you would put transposes on things so that you can transpose the columns to rows and then do the NumPy way. Okay. All right. Any questions on that? Yeah.
The reason why the image doesn't change to a black background with the white number?
Oh yeah. Okay. That's a great question, actually. So, so I would say by default, when you're working with images, the value 0 means like 0 brightness. And so that would correspond to a black background. And the highest number, 255, that would be a pure white pixel. And so, so in this case, when you look at the data set, you're going to have zeros out here, and then you're going to have some things close to the highest pixel in the middle. And that is just how the data set is. So this picture that I showed you earlier, I don't really remember where exactly this comes from, but this is kind of opposite for how the data is actually represented. So it's just, it's obviously if you want to plot things that way, you can, but almost always when you look at MNIST pictures, it's going to be white on a black background. Yeah. Okay, but that's a good question. All right. Any other questions? Okay. So, so here's just a little bit of code that shows how we can plot these images. So the main plotting command in matplotlib is imshow. And here we can write a little function that shows, or that will plot one of the vectors from our data set. So remember that our data set, as always, like when you download the data set, let's say you get an X matrix that has all your features. So every row is going to be a new data sample, so a new image. And then across the columns are the pixels. And so you're going to have 784 columns. So to plot this, you want to put it back into this image form. So we can tell it use 28 rows and columns, do this reshape command that we saw earlier, and then use the imshow command to plot that. And here we're telling it which color map to use. So it needs to know how to map the numbers from the smallest to the biggest number. It needs to know how to map those to brightnesses or colors or whatever. And you can choose from many different color maps. Like there's different colored ones and so on. But we're just going to choose this grays R, and that's going to give us this. And usually, when you plot things, there's these axis ticks. We're just going to remove those so that they're not annoying us. So that's what those commands do. Okay, and then this is essentially how you work with the data. MNIST.data. We'll set that as X. MNIST.target. we'll set that as y, except here, I can't remember what the original format is, but we're recasting this as a NumPy int 8 format. So these guys will be 8-bit integers. And to plot this, we just plotted 4 random digits. And so something that's sort of interesting or important with this data set is, I think if you don't shuffle the training data, I think it's organized by like all the images 0, 1, 2, and so on. So if you forgot to shuffle your data and you did some sort of like split it into training and test folds, it would be terrible because you would train on like, zeros and ones, and then you'd be testing on other digits and it just wouldn't work. So we're gonna do this random permutation, and then we're gonna use that to shuffle all of our data and make sure that we can easily work with it, and we can just pull out like the first 10,000 and work with those instead of maybe working with all 70,000 just to save time. And then because we shuffled, we know that we have a pretty good representation of all the digits in random order. Okay. All right. Any questions? Okay. All right. So we learned about multinomial logistic regression in the last unit. So that could be the first thing we try. And so here we're going to use 10,000 samples for training, 10,000 for test. We could use more, but it just takes longer. So just to save time, we're going to use 10,000. There's a few little things about how you pre-process this data that is actually important. If you mess them up, then things start to fail. So one of the things we're going to do is we want to convert so the data as it originally comes, it goes from 0 to 255, as I mentioned. And so usually it helps us, as we saw with, we talked about standardization when we talked about feature selection, lasso and ridge. So this data is very far from zero mean, and the numbers are quite large. And so for a lot of methods, it helps the method if you can get it into more of a zero mean type range and something maybe in a smaller interval, because it could be that some of the default parameters assigned by sklearn kind of assume that the data is closer to zero mean unit variance. So what we're going to do is we're going to divide by 255. That's going to get things in the range of 0 to 1. They're going to multiply by 2, so now it's in the range of 0 to 2, and subtract 1, now it's in the range from -1 to 1. So it's just in a more friendly range for some of the prediction functions. But there's sort of interesting things that if you're not careful about how you do this, so like the order of these operations matters, because, for example, this 255.0 is treated as a floating point number. This is treated as an integer. And the original data x, they are integers. So so like one of the issues is that this x is an unsigned 8-bit integer. And so what that means is the values go from 0 to 255, and if you add 1 to 255, it wraps back around to 0, right? So if you naively do this, where you multiply x by 2, then all those bright values actually kind of alias around, and it screws everything up. And so actually this gives you very different results than this. So here what we're doing is when you do this division, you're actually going to get floating point values. And now when you multiply a floating point value times an integer, it keeps it floating point, so it's fine. But if you do the 2 first, then you do this integer times integer multiplication, and that screws you up. So just like little things like this are important to know when you're working with Python and NumPy. Okay, any questions on any of that? Okay, so then here what we're doing is we're just splitting into training and test. And the reason we're not going to do things like k-fold is because this data set is pretty large, and it's already going to take us a little while to train a prediction model. So k-fold would take too long. We'd be too annoyed. So we're just going to do this very simple split into training and test. So the first 10,000 shuffled samples training, next 10,000 will be test. And then we're going to run logistic regression. So this is how we're going to set it up. So we're going to use the multinomial option. If you remember, that's what does this MLR, where you jointly design the weights and the intercept coefficients. You could also try OVR here. That would separately design them, and you would find the performance is a little bit worse, although it would run a little bit faster. For this one, we want to select a pretty fast solver, so we're going to use this LBFGS. Set it at 500 iterations. And if you remember, this is the value, the inverse regularization strength for the ridge regression that is in logistic regression. So we're going to set that at this number. Okay, and we run it, and what we find is the accuracy is 90%. So based on that table I showed you earlier, you know that this is definitely not state-of-the-art. It's not terrible because we saw like the linear regression method on that table, I think it was like 7.6 or 7.8 or something. So it's not too far from that. Maybe part of the reason is that we didn't use all of our training samples. We only used 10,000. Anyway, so that's the performance we get. It's okay, it's not great. And then if you actually look at the places where it's making errors, you can see it's making errors on things that we as humans would not really have too much trouble with. I mean, they're maybe a little bit tricky, but I think most of us would say that would be a 9, whereas MLR said it was a 1. This looks like a 4, even though MLR said 8. MLR said that this is a 3, and it said that this was a 5. So the question is, okay, what's going wrong? Is there something we could do a little bit better than how MLR is working on this data set? So to answer that question, let's first review a little bit about multinomial logistic regression, and then do a short experiment to give us some insight. So this is basically the procedure that we learned in the last unit to classify a test vector X. So in this case, it's going to be an MNIST image. So pictorially, it's like this. We start with this image. We make sure that this is converted to a 784-dimensional vector, so now we can kind of visualize it like that. And we're going to multiply this vector of features times a matrix that is going to have 10 rows. Each row in this matrix contains the weight coefficients for a classifier that is basically classifying as X as either in class K or not in class K. We have 10 classes total, right? So the first row contains the weights for in class 1 or not in class 1. It's that binary decision, binary classification. And here's the bias, the intercept. And then the next row would be the weights or the intercept for is it in class 2 or not, and so on. So we get in class 1, class 2, all the way to in class 0, let's say would be the last one. And so what we do in all linear regression schemes is that using this feature vector X and the coefficients for the kth binary classifier here, we compute these binary scores. We call them ZK. So these are the ZKs. And the way that we use these in logistic regression or multinomial logistic regression is that these things told us the probability of a particular model. So the model was this one. We called it the softmax. So you plug in the values from the Z vector into here, and if you have ZK on the top, then it returns the probability that this model thinks that this vector X is in class K. Okay, so when you sum up all those different probabilities, they all add up to 1. Also, they're all numbers themselves between 0 and 1. So that's essentially what this softmax is doing. It's taking a vector of real numbers, where the higher the Z is, the stronger the belief that it's in that class. And it's just mapping them to a PMF. It's just the simplest way to map a vector of real numbers to a PMF. That's essentially what the softmax does. Anyway, so from this, we can get probabilities on each one of those scores, or sorry, each one of those class hypotheses, and we just would choose the one that is the highest probability. So if the second class gives us the highest probability, we would say, okay, that's the best guess. But if you look at this, this is just a constant across all these z's. So really, you're just focusing on the denominator when you do that. And you actually can just look at the z's themselves, because the zk that leads to the largest class is actually just the largest zk. So if you want to just look directly at the scores, that's enough. You just look through these and you choose the index of the largest score. That is going to give you the same results. So that's just a review of how linear classification works, essentially. And for MLR, we just trained in a particular way to get those coefficients. Okay, any questions on that? Okay, so now we can do a little experiment. In the same way that we can take this vector, this vector of just grayscale pixels, and we can reshape it into an image to view it as a human, you can also take each one of these rows of weights and you can reshape them the same way into an image to view the picture of the weights. And the reason why that's useful is that intuitively we want that zk should be large when the true x is truly from class K. We want that zk to be the largest of all the different z's, right? And so if you think like how could I adjust the weights so that that zk becomes large for that particular class? Well, you probably want to make this weight vector look very similar to this x vector, so that when you do this inner product or pointwise multiply, that the large values in the weights hit the large values in the image, right? And then they become large. So that's sort of what you want. You want that the weight vector should look quite a bit like the images from these different classes. And so what's interesting is when you do this with 100 training samples, so we only train, let's say, with 100, and you plot the weight vectors, the weight vector for the class 0, for class 1, and so on, you actually can see the images sort of in there. So this really does look like a 0. And so, oh, by the way the color map here works is that this color gray would be 0. So this is 0. Anything lighter than that gray would be positive, and anything darker than that gray would be negative, I believe. Yeah, that's the way it should be working. In any case, when you look at this, you do see sort of a 0 here. You see a 1 here. You see a 2 here. You see a 3 here. You see a 4 here. So things are making sense, right? But what's interesting is when you actually repeat this experiment with all 1,000 training samples, it becomes harder to see those images. It's hard to tell that there's a 0 here or 1 here and so on. And so this helps us understand what's happening to multinomial logistic regression. So what it's doing is it's like based on those 10,000 training images, it's somehow determined that like to detect a 0, it's important to have this little white spot here, right? Because probably there's like some training image that had a little, for a 0, that had a little white spot there. And then for some reason, like this pixel was, unusually high for the 0s, and maybe it makes sense that there would be a dark one in the middle, because probably all the 0s right in the middle had nothing. But some of these other, so why is this dark and why is just right next to it light? It's kind of weird, right? It's just sort of an artifact of the training. In some sense, it's overfitting, you could say, to the training. It's focusing on details which may or may not be that important if you think like if my job is really just to detect zeros, like why is this a good pixel to emphasize and this is one I want to de-emphasize? Right? It doesn't make that much sense. But that's what happens. Same with these other digits. Okay, so that's sort of the motivation for what we're doing in this unit. What we're noticing here is that somehow when we give this method a lot of training samples, it's not really focusing on maybe all the right things. It's somehow getting distracted by this massive quantity of data. Is there some way to focus on a few important training samples instead of just like using all of them and somehow coming up with just some strange overfitted prediction based on all of them? That's kind of the motivating idea. So what we're going to do in this method is, in this unit, is we're going to develop methods that try to focus on just a few samples. They're going to be called the support vectors. They're the samples that matter most to do classification, and it will actually completely ignore all the other samples. So that's the main idea behind this support vector stuff. So this is a good time to pause for questions. Is this making sense, or any questions? Yes.
Is the top row or is the bottom row, or is it not related to the 90% success rate from the previous slide?
So, so I think I think on one hand you're asking like, yeah, which one gave the 90%? That would be this one. So now I'm not claiming that this one did worse than 90% or better. In fact, I'm almost positive this 100 samples did worse than 90%. What we're really trying to do here is just sort of notice a trend and inspire an idea rather than saying the right thing to do is only use 100, because actually no, this is going to be worse in terms of average accuracy than this. But we're just sort of noticing what happens to the weights. Okay, that's a good question. Are there some other questions? Yeah.
We mapped the x values between -1 and 1, but it doesn't mean that weights are going to be between -1 and 1. How are we plotting this?
I have to look at the code. Yeah, the weights definitely don't need to be. So it's going to be a matter of how it set the color maps. So I don't remember exactly what the code is doing in the demo, but you could check it out. So usually, like if you ask, like implot this this plotting command, sorry, imshow. If you just give it like an image to plot, it's going to probably by default scale, use a color map where the very smallest pixel, the most negative in this case, would be black, and the very largest positive would be white, and then everything else is just linearly in between. That's probably the default. I don't remember if there's any other processing, but I'm guessing, that because you can actually see how the color of the background is changing, even though I'm almost positive these are all zeros and these are all zeros. It's changing because when this was plotted, the max and min pixels were different, so the color map was different. Okay, yeah.
So is there any way that the data was like centered or shaped accordingly to itself before it was put into this? Or
Centered, you mean in amplitude, or what do you mean?
so like the numbers, like each image, so like if 1 0 was like slightly to the right, that would throw it off.
Yeah, so in this data set, they did a pretty good job of centering the images. Although, there's, and they did a pretty good job of making sure that they're the same size. Although it's impossible, because they have different shapes, it's impossible to really, they're not all going to look the same. So, but yeah, they did their best to center them and to scale them and to, I don't know, maybe they didn't try to rotate them, but you can see this is just a few examples. They have different thicknesses and different styles of writing numbers and so on. Okay, any other questions? Okay, so that sort of sets up the motivation for what we're doing in this chapter. And so next we have to kind of dive into some details, and eventually we'll see how we finally get this this idea of choosing just a few samples. But what we're going to do first is kind of step back and think about the geometry of classification. We've seen some of these pictures before more casually, but we're going to look at them a little bit deeper now. So one thing that we saw before is we saw that the decision boundary is, but sort of by construction, the decision boundary is all the values of the feature vector that gives you a score of 0, because 0 is right on the boundary between knowing whether it's a 1 or a -1, or which label it is. So this was the equation we saw earlier. And this is an important equation. We'll keep seeing it again and again. So in this picture, we have, let's say, red samples, blue samples, and this happens to be a linearly separable data set. So we can put, different lines or different hyperplanes in here that separate the data. But for these, particular choices of B and W, that generates a very particular line that happens to sit right there, and that's our decision boundary. So the first important point is that this hyperplane, this decision boundary, is orthogonal to the weight vector W. So here you can see, if this is the origin, the weight vector W is going off in that direction, and that is orthogonal to this boundary. We can prove that to ourselves. The way to think about that is, let's say you take any 2 points that happen to be exactly on the boundary. So they would both satisfy this equation for x1 and x2, right? They both satisfy that equation. So then notice that, okay, so if I have, let's say, 2 points on the boundary, then if I look at the vector of the first minus the second, that's going to go exactly in the direction of that boundary, right? So does everybody agree with that? Okay, so now the question is, can we then prove that this is true? That this is a vector in the direction of the boundary? Is that orthogonal, meaning that transpose W is 0? So the way that we do that is essentially just notice that this is just like x1 transpose W equals, or let me do it this way, x1 transpose W minus x2 transpose W. What does that equal? So from this equation, you can see that x1 transpose W equals minus B. So I have like minus B. But then over here I have a minus sign, so I'm going to have a plus B for the next one, and I'll get 0. Okay. So hopefully that convinces you that yes, this is true for any 2 points on the boundary. So that means that this boundary direction is orthogonal to this W direction. So that's an important fact. There's actually several important facts on this page. Any questions on that first one? Okay. So here's another important thing, is the values of the intercepts of each of these axes are things we can easily get. Okay, so why does the boundary cross the x2 axis at minus b divided by W2? Okay, so to answer that, any point along this this axis here, by definition, that means that all the other parameters are 0, right? any point along here, like x1 is 0. Or if you had, not just x1 and x2, but a whole bunch of all the way up to xd, and you looked at any one of these, it means all the other x's would be 0. So when you look at this equation, such that only one of the x's is non-zero, you get something like b plus, let's say that it's the kth x that's non-zero. That's going to multiply times its wk. But then because all the other x's are 0, they're going to, it doesn't matter what those values of w are. They're going to be multiplied by zeros, so they're gone. So then that gives you 0. And then you just have to rearrange this to find xk is minus b over wk. Okay. And this holds for any k. So it holds for this one when k is 2, or this one when k is 1, and so on. There are kind of strange cases where you can imagine if you tilted this whole thing so that the boundary was exactly parallel to one of the x's and it would never cross this one. What do you think? How could you reflect that in the coefficients? So if b and wk are both 0, right, then you get 0 over 0, which is undefined. So that's what happens in the case of the boundary happens to be like this. It never crosses, this axis. And it's because that happens. Or actually, it might even be enough to have, it's enough to have the weight itself go to 0, because it's sort of like asymptotically as you angle this backward and it becomes more and more straight, this guy goes farther and farther to the right, and it just goes off to infinity. So you don't even need b to be 0. I think you just need that to go to 0. Okay. So that's another important geometrical fact. We know what the intercepts are. Any questions on that? Okay. And the very last one is a little bit more complicated to explain, but not really too bad. So it's the following one. It's that the signed distance from any point, let's say usually you care about a training point, from any point to the hyperplane is a number gamma I that satisfies this equation. Okay, so let's figure out that. So let's say that this is the xi that we are focusing on. We want to know how far, maybe I'll put it over here. How far is that point from this hyperplane? Okay, so the way that we can do this is we can ask the question, well, how far do I have to move from that point in the direction directly perpendicular to the hyperplane? How far do I have to move in that direction until I'm on the hyperplane? Okay, and after I've moved that far, that is the distance. Right? It's very important that I move perpendicular, because if I say, oh, how far do I have to move in this direction until I hit the hyperplane? Well, then you might say the distance is this much, but no, that's not the distance. The distance between a point and a plane is the distance between that point and the closest place on the plane. So we have to move orthogonal, and then that's how we can do it. So essentially, this new point, the one that's exactly on the plane, we can construct using this equation. So here we have the original. This is how far we've moved. This, you can see, this is a vector, w divided by its norm. This is a vector that's in the direction of w, but I've scaled it so that that's a unit norm vector, a unit length vector. So now gamma times that is or I could say actually negative gamma times that is pointing in this direction, and it has a length or a norm of gamma I. So essentially, now I know that this is on the plane, and now all I have to do is I have to plug that into this equation to solve for gamma, and that will tell me how far that point is from the plane. So here's the equation from above. where all I've done is I've taken this x, I've plugged in this new one. So that's this. I know because it's on the plane, it has to satisfy this equation. And let's say I know everything here except for gamma I, so I can solve for gamma I. So what we can do is we just multiply this out, get b, and we get plus xi transpose w. And then the last term, you can see that we get w transpose w. What's another way of expressing that? The 2 norms squared, right? Now I'm dividing by the norm, so that cancels the square. So I just get minus gamma I norm of w. And finally, since that equals 0, I can just solve for gamma I, and we get this. Okay, so this is the distance from here to here. And it's a little bit different from a regular distance. Usually we think of distance as just purely positive thing. But this is a distance that, it could be positive, it could be negative. It sort of tells us the distance and the direction. Do I move in the direction of w, or do I move the opposite direction? Like if I'm over here, I would move here, and I would have basically something of a different sign than I would over here in terms of the distance. So that's that equation. And okay, any questions on that? Okay, and then the very last thing to notice is that I think you actually saw this on the last homework too. If you scale both the b and the w coefficients, nothing changes about the classifier boundary, right? You can actually see that just from the intercepts. So in this case, if let's say I double b and I double all the w coefficients, like this stays in the same place, right? Because the doubling cancels. This stays in the same place. Okay, so this doesn't change location at all. The only thing that changes would be the amplitudes of the scores. So if this is z and I double this stuff, then all of a sudden z would be twice as big as it was before I doubled it. That's all that changes, but the decision we make, which is the sign of z, that won't change. Okay, so those are just a few facts that we need to know, and then we'll put them together in just a moment. Okay, so this is a pretty important page, pretty important picture to remember. Oh, and when we scale it, we want that alpha is positive, because if you scale it with a negative alpha, you actually will change the sign of z, and then you'll flip your decisions. You don't want that. So as long as alpha is positive, you can scale b and w, and it doesn't really affect much. Okay. Okay, great. Any questions on anything? Yeah.
Is this like telling us how distinct something is compared to where we're deciding?
Are you referring to this?
Yeah, the gamma.
Okay. Yeah, so the role of gamma is how close we are to the boundary. So in classification, sort of intuitively, like the closer you are to the boundary, the harder it is to decide what class it's in. So the points that are far from the boundary are the easiest, right? So these guys would be like the easiest ones. They would have, like this one, I'm not sure for this example how it works out, whether these are positive and these are negatives, but let's say that these are positive, then this would be the highest positive value, this would be the highest or the smallest negative value. It'd be like that. Okay. All right, any other questions? Yes.
I thought, would it not be sufficient to use the score z to determine how far a certain data point is from the boundary, as opposed to gamma?
Well, so the score is the top, right? That actually is the score for that point.
Oh.
So you can see that it's like you do need to normalize by the norm of the w to actually get the distance.
I see.
Yeah, but yeah, the score tells you like an unnormalized version of that. Yeah, so the score, just as gamma does, the score itself tells you how easy or hard a point is. Like if the score is close to 0, it's hard to classify. If it's far from 0 in either direction, positive or negative, it's easy to classify.
So he's using gamma to find out the samples that give the maximum.
Yeah, so we're preparing to think about gamma as a way of figuring out which samples are the hardest to deal with so that we can focus on them. And that will let us not get as distracted by the easy ones. So that's kind of going to be what happens in this unit, exactly. Yeah, we're just working up to that mathematically. Okay, great questions. Any other questions? Okay. So, so another concept which we've talked about, but now we're going to be a bit more specific about is linear separability. So if you remember, linear separability was the idea that it's a property of a data set. If your data set is linearly separable, that means it's possible to place a line, or in general a hyperplane, to pass it through the data in such a way that all the samples in one class are on one side of the line and all the samples in the other class are on the other side of the line. Another comment we made earlier was that, generally speaking, when you find a linear separable data set, there's actually many different hyperplanes you could construct which cleanly separate it. So it's not going to be a unique thing. And of course, the weights and the B's and the W's, they are exactly what are parameterizing those boundaries. Okay, so we're going to, just for tractability, so that the equations look nice, we're going to assume binary plus minus one training data rather than 0, 1. Conceptually, you can do everything for 0, 1s too, but it's just the equations are messier. Okay, so this is rather than 0, 1. Okay, so keep that in mind, binary plus minus 1. And so now we're gonna define linearly separable in a mathematical way. So I think probably the easiest place to start would be just to think about the scores. So let's say the score for the ith training sample, that's B plus xi transpose W. And so if the label yi is 1, we want, let's say that the score is positive. So epsilon is going to be some strictly positive number. And so we want this to be greater or equal to some positive number. So that's what we want. So on one side, all the yi equals 1s. Meanwhile, if you look at the scores of the samples labeled as minus 1, they should all be negative scores. So all of them should have negative z. They should be on the other side. Okay, so it's probably the easiest way to think about it, but it's a little cumbersome. It involves two inequalities and this parameter epsilon and all this stuff. But I just want to stop there. Is this part clear, or does anybody have any questions about how we're getting this? Okay, everybody's good with this? Okay. So the first thing we can do is, leveraging the fact that the labels are plus minus 1, we can actually rewrite both of these as one equation. That's this. So it's because if I multiply, if I multiply this by yi when it's 1, nothing changes. But if I multiply this by yi when it's minus 1, then the sign of the equality changes, and the sign of this changes too. And so essentially we can put both of them together as this equation, or this inequality. Okay, so we're saying if there exists a b and a w and some constant epsilon such that this holds for all your training samples. Okay, but now what about this annoying epsilon? Can we get rid of it? So if you imagine dividing both sides of this by this positive number, well, the inequality does not change signs, but you would just get an epsilon dividing the b and the w. So now that's essentially like saying, instead of the BW classifier, you have this b over epsilon, w over epsilon classifier. And we said that that's sort of an equivalent classifier in the sense that the boundary has not moved at all. So from another perspective, like if you can find a b and the w that this works for 1 epsilon, then just by scaling that b and w, you can get it to work for any epsilon you want. So let's just choose epsilon equal 1, the simplest choice. So that's how we're going to define linear separability. So this means there exists a b and a w such that this equality holds for all I. So you could think of this as a sign-corrected score. So you're taking the score and you're multiplying by this plus minus 1y, and you want that the sign-corrected score is always 1 or larger. There should be some b and w for which, you can find some b and w for which that holds for all your data samples. That's one way to write linear separability. Okay, that's in fact how we're gonna write it. So maybe I'll highlight this expression. Okay, so that's our definition. Okay, any questions? Yes.
So the epsilon is just a guarantee that none of the points sit on that.
Yes, right, exactly. We don't want, because like, yeah, you can imagine if you put your data all on a line, there's no way you could separate it. So it just needs to be epsilon away from that. Yeah. So the original definition of epsilon was just to say it should be pushed away, but then we managed to get rid of this epsilon so that we don't have to deal with it later. Okay, yes.
When we assume that it's binary plus or minus 1, is that it needs to be plus or minus 1, or would it equally work if it was 0 and 1?
So we could rewrite all these equations for 0, 1, or any other pair. They just don't look as pretty. Yeah. So it just looks prettier when it's 1 and minus 1. Okay. Great. Any other questions? Okay. So so finally, what we can say is we can kind of merge this equation with this definition. So if you think about it, this is a way of writing the score as gamma I times the norm of W. So I can substitute for this, I can substitute gamma I divided or times norm of W. And when you do that, you get this. And so now you have like a sign-corrected signed distance should be greater or equal to 1 over the norm of W for all your points. And this 1 over the norm of W is kind of a important quantity that gets a specific definition. It's called the margin. And you can think about it as a lower bound on the minimum distance from any training point to the boundary. Okay, so in this picture here, sort of an illustration where you can see that there's samples from one class here, samples from one class here, and the boundary is here, and there's what you call a street. You can think about this as a street, where you can fit that street in perfectly between all your training samples. And the distance, or the width, the half width of the street is this gamma. So, or at least it's maybe at least a lower bound. So if you remember the gamma I, we can think of that as the distance from each of these points to the boundary, except it's the sign distance, so some of them are negative and some of them are positive, so we get rid of that sign discrepancy by multiplying by these binary yi. So the remaining sign-corrected distances now, they should all be positive, but even more so, according to our definition of linear separable, it means we were able to find some b and w such that that sign-corrected distance is greater or equal to this margin parameter, 1 over norm of w. Okay, so imagine now that instead of choosing the boundary like that, I chose the boundary over here. Do you see how the width of the street has now changed? It's much narrower, right? Now it's like that narrow. So this classifier has a worse margin. And you can see it's a worse classifier too, right? Because if I put the classifier here, even though it's still linearly separating the training data set, maybe there's going to be a test point, over here, and it would fail on that test point. So this is, so the way that we're constructing it here is we're being careful to place it in such a way that's sort of maximally robust. We're trying to be as robust as possible to basically push the training as far as possible from that boundary. That's the whole idea behind this family of classifier designs. All right, so any last questions here? Okay, so we're out of time for today, but basically what we're going to do is we're going to figure out, set up an optimization problem that gives us exactly this. That will be what we're going to do on Wednesday. See you guys then.